O que não pode é a deliberação depois, né? Quando a gente for falar. Aí.
Depois de fazer o computador, depois de fazer o microfone.
Beleza, então eu vou. Vou ativar o microfone agora também. Ver se sai alguma coisa. Top. Vamos ver se tá passando de dados.
Tá de boa então, né? Top, pô, deu certo. Acho que eu vou startar stream na Bex então logo.
Topzera.
Tá pegando o meu barulho.
Ele tá pegando o mic do PC ou será que tá pegando esse daqui? Porque esse daqui ele é melhorzinho. Provavelmente desse daqui, né, mano? Não sei. Aí também já é querer melhorar demais. Aí tem que pagar superchat pra fazer. Ele tá pegando o mic do PC ou será que tá pegando? Pô, tá mó limpo no volume, tá de boa. Deixa eu... Cadê o meu Alex? Ah, porra, ele tá na janela errada, filho, de novo. Se acontecer isso na hora, vai ser uma vergonha, mano. Deixa eu achar aqui rapidão. microfone, então. Pronto. Caralho. Beleza.
Pronto, acho que tá setado. Já tem gente na sala. Então já tô. Já que eu não tô no padrão, né? Porque eu tenho uma sala aqui. Vou só fechar o som por enquanto aqui na sala. Caiu na câmera, eu vou andar de boa. Não, mas de boa, a professora é brasileira. Ela é uma professora, não dá pra ver. Sério, então eu cantinho aqui pra não aparecer mais. De boa. Pô, acho que eu vou tirar a mochila aqui só pra ficar mais estético. Tá um perigo essa câmera pegando as costas, né? Tá um perigo essa câmera pegando as costas. Tá de boa, vou voltar lá pro início.
Testing the sound, 1, 2, testing the sound.
The best is that you can sit on the front of the jury. How many are you? Like 5 maybe? Maybe just arrange it. On va faire une grande table devant. Il y a 5 ici. Oui, 5 physiquement présents. Vous les mettez on fait une grande table comme ça. D'accord, ok. Celle-ci, je vais la coller là. D'accord. Peut-être. Ouais, ça va aller, faire le 5.
Parce que si c'est là.
Oui, c'est là, ouais. Vous voulez faire un truc plus comme ça?
On simplement rééquilibre.
Oui, mais peut-être 5, il faudra un peu plus tard.
Oui, simplement.
On va décaler comme ça?
On voit droit.
D'accord. Je trouve celle-ci un peu plus loin.
Can you open the mic for the...
Yes, sure. Bonjour Marc.
Bonjour.
Ah, tu m'entends, ok.
Je vous entends. Tout à l'heure, vous entendez.
Hello Mylène.
Hello.
Thanks for being here. Thanks for being there. So we have a small room here that we are trying to organize. So the room is a bit small, so but it should be okay.
Il n'y a rien de spécial. Peut-être que c'est un jury en sous-tutelle, tout ça.
Non, je crois
Il y
pas.
aura le formulaire dont parlait Robert.
This is for you, David.
Okay, I also print.
You have it.
Yeah.
Whatever. I can take you.
Je me déplace.
Non, non, c'est bien ça que je fais.
Les formulaires sont là.
Good afternoon, everyone.
Hello, Adrien. Did you make some tests for the sound?
Yeah, like, can you hear me clearly?
I hear you very well, yes.
Okay.
And the jury? Can you hear the jury as well?
Yes, I can hear you as well, Christine.
Okay.
Just 1 second. I think I'll get headphones. It's better.
Okay. Or keep it there when you present.
I have one there.
Tu veux le faire en avant?
Okay.
Ok. So I propose that we start this PhD defense, and first I will start by presenting the jury members, and starting with the members who are remote. So we have Professor Milen Farias from Texas State University. Then we have also in remote Professor Marc Antonini from the University of Nice Sophia Antipolis, and Professor Adrienne Monteneani from French University in Brussels, who was a rapporteur of this study. And then the other rapporteur was Professor Gauthier Lafruy from Université Lille de Bruxelles. And the third examiner is myself, Luce Corin, I am a professor at Université de Rennes, well, in Rennes, and in IITR. And also, I will present now the advisors of the thesis. So, Professor Johan Tabus from the University of Tampere, and Professor Robert Bregovic from University of Tampere too, and who are the co-advisor with Professor Christine Guillemot, directrice de recherche at INRIA. So now, Davi, you have 45 minutes to present your work.
Okay. Well, so thank you for the introduction, Professor Lismoha. So, good afternoon, everybody. I'm Davi Freitas. I'd like to present this work on this double degree between Tampere University and the INRIA Rennes. And here we focus on the exploration of Plenoptic 3D scene representations. So first of all, what do we mean when we say sensing and reconstruction? Well, if you take, for example, a practical application where you want to render a 3D scene, you want to capture an object from a person, and you want to convey that through a network. So the network here means ways where you can convey information, not a neural network. And here on the decoding side, you decode the information, and you want to render with some specifications that have some priorities in terms of immersiveness. So that can be visual depth cues, motion cues, but also view-dependent colors. And when we're talking about color, the light is inherently connected. And as is the foundation from what the visual sensors, be it the eyes or a sensor device, percept and interpret a scene, you want to understand its behavior, allowing for a more efficient display design. So considering that, the Plenoptic function aims to represent the light's intensity with any given direction by a 7D function, where the x, y, and z are the spatial coordinates, then theta and phi are the viewing direction, the lambda is the wavelength, and the t is the time. And this allows the representation of non-Lambertian reflections, where the reflections for a certain incident light will vary independent of the angle of the observer. So here on the left, a Lambertian reflection is going to have an incident light, where the reflected rays, they reflect equally in all the viewing directions. And then on Lambertian, on the right side, you can see how they are view dependent. And how is that manifested visually in the scene? On the left, you can see a scene with Lambertian reflection. And on the right, you can see the viewing direction that is encoded on the color attributes. So these Plenoptic scenes, they can be represented explicitly or implicitly. So explicit has this name because of how the information of the scene is directly encoded into a structured and interpretable format. And the biggest exponent of this kind of approach, this kind of paradigm, is the Plenoptic point clouds. And the scene is implicitly defined as a continuous function of spatial or appearance parameters. And those include the neurovergence fields, also the Gaussian splitting. And with that in mind, our contributions throughout this work, they explore the methods that they explore both approaches, and finishing with a comparative assessment between these paradigms. But first, we need some definitions. So going for the explicit scene representations first, a point cloud represents a 3D scene with a list of coordinates and associated attributes, and generally it's done with a color. These coordinates, they are often voxelized into coordinates of power of 2, And that's for ease of representation with hierarchical structures such as octaves. So as a Plenoptic point cloud extends this kind of information, but instead having multiple color attributes instead of just a single one. And that is directly related with the Plenoptic function, where the number of RGB triplets that we have for the multiple colors are related with our viewing direction dependent information. So the biggest advantage is that it provides more realistic representations, so we can have these non-numbration scenes, but has a couple of drawbacks, namely the increased volume of data, but also the discrete representation of the Plenoptic function. And considering the scope of our thesis, because of this drawback of the increased sizes, we want to explore the reduction of this kind of information. So first, a quick overview of some coding fundamentals. The Plenoptic point cloud compression extends solutions of existing point cloud algorithms. So on the geometry side of things, the voxelized point clouds are often coded with these hierarchical structures called octaves. And those, each node has either 0 or 8 children. So starting from level 0, where it's playing the whole scene, we can go up in levels as increases the resolution, and allow us to traverse the branches with additional children until we reach the leaves. And on the attribute side, we have the region adaptive hierarchical transform, also known as RET, and uses a sub-band decomposition on the octave disposition. So traversing from the leaves, we have groups voxel into larger ones by accumulating the weights occupied on the sub-branches. And we can also direct this transformation so we can create low and high frequency components. And with this increasing industry interest in immersive content, MPEG define a set of requirements that result in two main point cloud strategies for compression. So the first one, the video-based point cloud compression, the VPCC, normally suited for dynamic scenes, so they project the 3D data into 2D images, and they can use existing 2D video codecs to do that. And the other one, the geometry-based point cloud compression, also known as GPCC, is where the content is encoded directly in the 3D space. So for the Plenoptic point cloud side, the first pioneer solution was the RET extension for directional encoding, where it uses a transformation of colors using a Caroline wave transform in 1D. So this solution was called the RET KLT, and later on, other works extended this kind of framework. So either using a clustering of specular and diffuse components, either using a different parameterization to 6D coordinates, and also by doing compliances with both MPEG PCC standards. So either using multi-view HVC to encode the PCC, or giving a secondary payload as Plenoptic information, so have full compliance. We noticed there was a lack of contributions with the GPCC side of compression, and that leads to a first research question, first contribution. So how can we leverage these PCC standards, in particular GPCC, to compress these Plenoptic point clouds? So our goal is to have a framework that's GPCC compliant to explore these Plenoptic attributes, and then we can use these existing efficient coding techniques to achieve low bit rates and competitive state of the art. So our proposed idea is, in short, to have a differential transform in the Plenoptic colors, use predictive coding, and then use the GPCC's arithmetic coding to create the bit streams. So consider a point cloud as a list of voxels with NC cameras, as such having NC RGB triplets. We have a color vector, NC color vector, which is transformed with a linear transform HC, and this creates a signal S. And the HC here is also the 1D Caroline wave transform, as done in the RET KLT, and creates a NC by NC, NC times NC covariance matrix. And then this transform coefficients are sent for predictive coding. So in GPCC, they proposes two predictive attribute coding schemes. So the first one is based on RET, also known as upside down RET, and is also called URET. So it calls its name because there's a top-down approach. So instead of computing from the leaves to the roots, it does the upside down. So it goes from the roots to the leaves. And the second one is based on level of detail, LOD, which is called the predictive and lifting transform, and does a refined levels based on distance thresholds, including distance thresholds between points, and use this generated context to predict the points in higher refinement levels. So we encode these SK saddle coefficients with the state-of-the-art attribute schemes, and we use these SK sets, each one as a point cloud. So the first one uses the ret-based approach, which you call proposed method 1. And the second one uses the LOD, which you call here the proposed method 2. So for experiments, use the 6 Plenoptic point clouds that they range between 12 and 13 Plenoptic colors, so 12 or 13 RGB triplets. And we have resolutions of depth 10 and 12, which means they are voxelized into grids that have 2 to the power of either 10 or 12. So the comparison between the proposals 1 and 2, so the reds and the LOD, we also compare with the multi-view HVC for VPCC, and also the red KLT. And you can see how the significant gains can be noted for method 1, particularly in the high bit rates. And using comparisons also from the depth 10, we also evaluated the proposal 1 and 2, and also red KLT, and also show that we have superior gains in terms of weight distortion. So as visual comparison, you can see on the top right, we have the red KLT, and on the bottom, we have the two proposed methods. So on the left, we have the proposed method with the red, and on the right, you have the LOD. And although the LOD provides a slightly higher PSNR metric, it also produces bigger models. And because of that, it gives a slight loss in terms of weight distortion. So to summarize, we propose that this is GPCC-based solution using the division transform to predictive coding and also GPCC encoding. And our proposed method 1 provides these coding gains for both types of Plenoptic point clouds. But however, these are explicit representations that have some limitations. As I said before, they have some scalability problems because you need 1 RGB triplets per camera view. And that increases the difficulty for novel view synthesis. So if you want to create to view the scene from a certain point of view, and you don't have exact RGB triplet corresponding to that view, you need to do some kind of interpolation that is up to the renderer. And this framework also do not include occlusions because the KLT transforms, they need the vectors to be on the same size. And because of that, the points that are occluded, you still need some information so they can be transformed. And this led us to explore these drawbacks and led us to explore these Plenoptic parameterizations using implicit solutions. So going a bit more in depth, these implicit scene representations. They are continuous functions that extrapolate geometry or appearance in the scene. So they are suited for applications as novel view synthesis because of that. And they are often parameterized in neural networks. So the biggest exponents that these solutions include, they include NERF, Plenoptris, and 3DGS. And here we pay special attention to the two latter ones, due to two reasons I'll explain shortly. So the neural radiance fields was the first big exponent where the scene is encoded implicitly in a neural network. So you have for a 5D coordinate, there you have the position, the theta and phi position that is defined by the position of the camera. And you have the 3D position, the X, Y, and Z, and use that to encode into a neural network. So each ray, they have multiple samples, they're going to be encoded in the network. It's going to generate information of RGB and also a sigma parameter, which is intensity. And we can alpha blend them to create a pixel color. So to render an image for a certain viewpoint, we have to apply this process for every pixel, so we can create like a render image of the scene. So it has a couple of drawbacks, this kind of design, which first it has a heavy training cost, since you have to train one for each scene. But also the rendering speed is slow by design, because you need for every pixel, you need to put multiple queries into a neural network. So how can we speed up? So speed up methods, they consist of either reducing the number of queries to the neural network, and by this you can do it by using spatial distributed structures, so you can do some localization, or you can make each query less expensive, and you can do that by making the neural network smaller. So Plenoptris does the former, so it stores rendering parameters into an octree. But to do that, you need a color that is view independent. And with that, it outputs spherical harmonics instead of RGB triplets. And for that, it modifies the initial nerf network into a nerf SH, which outputs the independent colors. And later with these parameters, you can store into this altered, in this localized octree, which we call Plenoptic, and you can use the same rendering schematic as nerf, so it has the same loss, so we can optimize the same as nerf. So this results into a speed of over 3,000 times over the original nerf, but it also creates model sizes that 200 times larger because of these auxiliary structures. So can we maintain this rendering speed and quality while reducing their sizes? This is the biggest drawback that they have. And that leads us to our second contribution. So our goal here is to provide a compression framework that maintains the rendering speed, the rendering pipeline that this model has. And we propose that by working on different stages of optimization and also providing a compression step. So more in detail, we work on each step of the pipeline, of the creation pipeline of the model. And we also add at the end a compression stage, so we can reduce the size into smaller bit streams. So in our first step, the neural network training, the last function was first altered to improve the geometry when working with the octree itself. So first we add a total variation regularizer to increase the smoothness of the geometry output that is output from the network. And also add a sparsity loss that was changed to the Cauchy loss to further reduce the number of points for the later stage of the method, so we can ease into smaller models. And on the structural optimization, the first thing that's important to notice is the distribution of the parameters into the model. So here you can see that 95% of the model size is related to the spherical harmonic coefficients and also the sigma coefficients. And we want to reduce the number of occupied voxels during this optimization, so before doing any compression. And first you do a threshold of the sigma values using the estimated alpha values, so use the step sizes of the octree. And after we fine-tune this distilled octree, so we can improve the method before sending to compression. So in the compression stage, you compress both the sigma and the k coefficients. So how we do that? We consider it as a point cloud, where each point has a list of attributes, and each of these attributes are the rendering parameters that we need to render this model. So in short, we need the density and the spherical harmonic parameters. And this can be seen also as a Plenoptic point cloud with multiple attributes. And because of that, we can use the schematic that we created for the explicit representation for this implicit representation. So we can use the schematic that we proposed in the first contribution, so we can reduce this correlation between the different parameters. So in our experiments, we first start with the neural network step, where we can see a slight baseline gain over the original solution. More importantly, for the later stages, we have a geometry that's more smooth and makes it easier to prune. So for experiments regarding the threshold that we apply on the sigma values, each point here has two upper and bottom points. So the point on the bottom is before the fine-tuning is applied, and the point on the top is after the fine-tuning is applied. And you can see that for these scenes, certain values of sigma, they keep a similar rendering quality after the fine-tuning, while the points can be down to half of the original ones. Also, when you compare to the whole data set, we also can see on the table that the threshold in this fine-tuning process can reduce the number of points, while also keeping the quality of the final renders into a similar value as the original. So for the compression experiments, so we have the rate distortion, where the rate is the size in bytes, in gigabytes, and the quality are done in the PSNR of the rendered views. We show that on the right here, we have the baseline for the Plenoptic solutions. So they have the two original ones there with either 9 or 16 spherical harmonic coefficients per color. And these two methods on the bottom, there are two proposed solutions for compression based on the attributes of the Plenoptics. And here you can see the other ones are the ones that we proposed. So you can see using 16 harmonics, with the rat-based that we proposed in the first scheme, you can see some quality gains, especially going to lower rates without a significant decrease in the quality of the renders. So in the overall model quality evaluation, we have a reduction of over 50 times when you compare the lossless compared to the baseline. And also is still having a slight increase in quality because of a neural network contributions. And when you have the lossy, for the lossy attribute encoding, we have a similar quality in terms of the baseline, while also having models that are 50 times smaller than the original. In the qualitative evaluation, we have the ground truth here. You can notice that the white hole inside the tractor's bucket. You can see how with the original Plenoptic on the top right, has because of the excessive number of points, the point is less sharper, and that's because of the points that are not significant for the certain view. And once you start the pruning with the bottom left, we can see how the point is sharper, closer to the original image. And when you apply the lossy compression, we can still have a significant quality, but while having methods that are 50 times smaller. So in short, we propose changes to this Plenoptic pipeline with the goal of reducing the sizes. So we provide a size reduction of 50 times. We reduce degradation in the lossy attribute coding. And we provide these improvements in distortion by reducing also the size of the octrees before doing the compression. But one of the ways that we can improve significantly these bit rates is by improving this pruning algorithm before doing the compression. But we have a certain kind of concern that we want to have a certain flexibility of representation. So we don't want to constrain to a single type of modeling. And we do that because the state of the art for Plenoptic scene representations, they evolve, it's a fast evolving field. And if you have a pruning method that's too specific to a certain model, it can lead to a quick deprecation. And indeed, during our work, the 3D Gaussian splatting was a solution that appeared and proved to be very competitive. And it does a slightly different paradigm than ERF by optimizing the scene without a neural network, but actually optimizing over 3D Gaussian kernels with a certain covariance matrix sigma, and me. And basically, what it does, it has 3D ellipsoids with the centroids, and it represents this kind of covariance by having rotation and scaling matrices. So these 3D kernels, the main concern is how to rasterize them into 2D. So because of this lack of neural network and the optimization directly on the ellipsoids, it has a high rendering speed, and it also proves to have a rendering quality because of this kind of a rasterization that it does. So it has what we call this dynamic splatting. However, it tends also to produce excessive number of Gaussians. So you can also reduce the models by doing the compression, but also the pruning comes into play. And that leads us to a third research question, which is, can we model the pruning so we can fit also this Gaussian splatting in addition to the Plenoptic? So a third contribution then is to propose a pruning framework that uses underlying geometry, so we can also apply for different methods as long as they have this underlying geometry. So we propose to do that by computing the visibility of the 3D scene. So we can have during the training some kind of visibility information, and we can prune only the less visible elements. So we further combine this pruning with existing state-of-the-art compression algorithms, so we can also show if we can achieve smaller bit rates than the state-of-the-art. So here's our proposed framework. So when you have a training setup with a set of cameras D, each pixel can have a set of points in the scene. So the thickness parameter defines the tau points that are the closest to the camera. So we can define these tau points as if they are visible or not. So that's why it has its name, because it adjusts the thickness of the object. So we compute this information into a visibility mask O. It has n rows, it corresponds to the number of points of the scene. With regard to the k cameras, they are in the column of this visibility mask. So thus it creates n by k, n times k occlusion matrix. So we can also remove additional points by looking for each row, how many cameras this certain point is visible. And we do that if we create this MV parameter. So if it's under a certain amount, it's only visible for any cameras or less. We can also prune them. So in short, for the scale rendered views, we have this set of cameras. We compute this visibility by doing the forward projection of the points into the 2D. And then we can detect potential occlusions, creating this visibility mask. And thus we can apply this visibility approach both in the Plenoptic, but also in the 3DGS. So in the Plenoptic, how we embed that into our pipeline? We introduce this pruning after the structure is initially extracted, and also initially optimized. So after we do this visibility pruning step, we do extra fine-tuning step before conveying for compression. And here, in addition to this thickness and MV parameters, because the Plenoptic has a fixed type of splat, which is the voxel, the voxel resolution is also considered. Because if you have a too small of a resolution, if you have a resolution that provides too small voxel sizes, so it's a very high resolution, it can create holes if the points are not enough to fill the scene. But if the voxel sizes are too large, it can make the scenes to appear blocky. So in the 3DGS side, we embedded this in the optimization jointly with the multiplication of the Gaussians during the training. And we also add a regularization term to the loss, which is regarding the scaling matrix. So we can encourage the Gaussians to be as big as possible without compromising the render views. And for compression, we combine with existing compression algorithms. So for the Plenoptic side, we propose the compression scheme that we introduced in our second contribution. And on 3DGS side, we use two state-of-the-art compression approaches. So the first one targets strictly the color attributes and the Gaussian parameters. And the second one also reduces the number of points. So they also reduce the number of Gaussians, so there's also a certain kind of pruning that we can combine with ours. So for experiments, we first analyze the pruning of Plenoptic. So first, you want to have a set of optimal operation points regarding the three parameters that we set for the octaves. And we use this set of points to generate optimized curve that we can compare to our contribution that we performed in the second contribution. And here you can see as you start to go into the lower bit rates, where here the rate is not in bits, but actually the number of points of the model, so before being sent for compression. You can see how in the mid to low resolution, it has a certain advantage to our contribution from the second one. And also, ideally, we wanted to have a model that's better in terms of rendering quality, but we also wanted to be more accurate in the geometry, the underlying geometry. So we are sure that the points that are being pruned are also important for they are close related to the ground truth. So we provide a certain metric in relation to the ground truth, which is the receiver operating characteristic curves, the ROC curves. So here it works by having the true positive rates on the y-axis. So it has the ratio of the ground truth points related to the model that we're analyzing. And in the false positive rates in the x-axis is the ratio of the points that we are working with. There are no corresponding points in the ground truth. So ideally, we want to be on the upper left, which means that we have a good correspondence with the ground truth without a huge amount of points that have no correlation with the ground truth. And here you can see how again, going into the lower bit rates, our proposal seems to outperform our simple pruning step that we proposed in the second contribution. And by performing also rate distortion analysis on the rendered views and using the bit rates as a measure of rate, we also compare again with the threshold that we did on the second contribution. And we can also see that, especially in the low bit rates, there is a certain performance of our proposed method, even though it's marginal. For the Gaussian splitting side, we first analyze the number of Gaussians that we do have per iteration. So here you can see the methods our method by changing the parameters of the MVE. and comparing the vanilla 3D and the state-of-the-art proposal that provides also a certain pruning. So just by comparing these standalone versions, we have as our attribute increases, the average attribute increases, the pruning becomes more aggressive. So you can reach points that down to 1/3 of the original Plenoptic, the original 3DGS. And but here only shows the number of Gaussians. It doesn't show any information on the random quality. So that's why you also have an additional table to compare also in terms of random quality. So you take an example scene. We also compare the same models. So here we compare in terms of Gaussians. You can see for the values of MV, they are higher, so more aggressive. You can see the Gaussians, they reduce by almost 4 times compared to the vanilla model. But the quality metrics, they also do not reduce significantly. Here also have a PSNR, this bitrate comparison. So here we already combine our solution with the state-of-the-art compression methods. So now we can have the bit rates, the bit streams to compare the state-of-the-art. So here we can have in blue and green our methods combined with the corresponding method with the same format, the same shape. So you can see how in the first solution, the Lindemeyer solution, we have a pretty similar rendering quality in terms of PSNR, but also having smaller bitrate sizes. And in the Lee solution, we also have the same, slightly lower, but we are working here in ranges that are very small in terms of PSNR, so it's less than 1.1 dB. And here in the average quality metrics, it shows the average for all the scenes. So you can see the PSNR when you compare our solution when compared to the combination of them and the standalone. You can see there's a slightly decrease, if so, in terms of quality. But the number of points, they also reduce significantly. And thus the sizes, they also reduce by a fair amount. And indeed, when you have the subjective evaluation, you can see here on the bottom left, the 3DGS, the vanilla 3DGS, which has almost a 70 megabytes for this size. And here on the middle column, we compare the standalone state-of-the-art solution and on the bottom, the combination of that solution, the compression solution, with our pruning. You can see as the model not decreases, but slightly increases in terms of quality, but we also produce smaller models. And likewise for the last solution. So in short, we use this visibility of the elements to allow for flexibility with regard to the model choice. So as long as there is an underlying geometry for the model, we can do this kind of approach to prune them. And we are able to produce fewer elements with minimal quality losses because of that. And so we can compare the state of the art where we show that almost a 40 times compression ratio over the vanilla 3DGS, but with less than a 0.5 dB decrease. And compare the state of the art approaches, we can produce models that are 1.4 times smaller with less than a 0.1 dB loss. So we are able to do these comparisons in terms of ridge distortion, but these are only between the implicit methods. So we can't really compare as it is with the explicit methods. So can we provide a way to compare these two approaches, these two paradigms with a common framework? And that leads us to our last contribution, which is a framework to compare this kind of approaches. So why is this difficult to compare? So first, they are normally used for different purposes. So the implicit approaches, they're often used because of this advantage to compute the graphics for novel synthesis. The explicit approaches, they're often used in coding and encoding contexts. And so the model quality, because of that, is normally evaluated with different metrics. So the explicit, since you have the explicit information, these metrics are evaluated directly into 3D space. But the implicit, they are normally metrics over 2D rendered views. So, and also the process of capturing these Plenoptic point clouds is also difficult because you need the original information of the images so we can color them. And that also causes a reduced amount of existing data. So here we propose two main contributions. So the first one is propose a way to compare this Plenoptic model of both explicit with the Plenoptic point clouds, and the implicit with the new regions fields or the 3DGS, the Plenoptries. So we do compare them in encoding context, which means that we compare them on the training views, not on their capacity of creating other rules. So we do this comparison in terms of rendering quality and also compression efficiency. But also, in order to do that, we provide a pipeline so we can generate this Plenoptic point cloud systematically. So we can also increase these data sets and compare with the same data sets that we can also use for the implicit methods. And finally, also have because we don't use a 1D transform anymore, and we have this kind of visibility computation. You can also use the occlusion maps to better encode these models in the explicit side for the Plenoptic point clouds. So here's our framework design. So on the top here is the conventional way that implicit methods use to generate novel views. So we have a set of camera poses that you use into the rendering of Blender. And with a mesh model, you can generate render views. And these render views, you can use them as well with the camera poses to train a neural network or certain kind of representation, such as a 3DGS. And this 3DGS is gonna render a new set of rendered views. So here, since you are encoding context, the set of rendered views that we want to render is the same as the one that we train on. So it's the same set. So here on the bottom is what we propose with the Plenoptic point clouds, where we convert the meshes into colorless point clouds. We colorize them to create Plenoptic point clouds, and then we use this method to generate rendered views so we can directly compare with the implicit side. So we have a few steps. So the first one is to extract the mesh into the point clouds. So first, we have this dense set of points from the Blender models, and we want to sample them into a voxelized spatial structure. So they will have, because of that, different resolutions. And then we can sample them through different algorithms. So the three different ones that we do test is the triangle splits. So basically, it split triangles once the longest edge is smaller than 0.1 voxel, 0.5 voxel, so half a voxel. The Poisson disk sampling, which is it's a B-noise-based solution. And they're area-based, and basically it samples the points based on the size of the triangle area. The second step, we need to colorize these points. So in order to colorize, we have the set of the RGB the images that we use to train on the implicit side. And we can use this to create K RGB triplets, so we can have each point of the Plenoptic point cloud. So if X is a point in 3D space in the world coordinate system, first we need to forward project them in the camera coordinate system. And we use the extrinsic matrix for that of the camera, so the pose. And then we use the intrinsics of the camera to project them to the 2D render views. So with these pixel coordinates, we can normalize them at the depth. And this forward projection estimation is gonna give the pixel sizes. So the pixel sizes, again, as we did in the last contribution, we can estimate a certain kind of visibility for each one. So here we only take the first point, that's the closest to the camera, as a non-occluded point. And all the points, they are also projected the same pixel, but farther from the camera, from the pixel, they are marked as occluded. So again, we create n times k occlusion matrix, O. But we also can use this occluded voxel to also fill the average of the non-occluded views. So we can create also RGB main. And this RGB main allows us to have a certain backwards compatibility with the conventional point clouds. And you also use this occlusion mask to also better optimize our encoding framework. So use the MPEG's GSTM, which is a model that's based on the GPC Kone standard. And we use these non-occluded voxels to create sub-point clouds. So say, for example, you have 5 points, but they are only visible for certain cameras. So for example, on the green here, we have points that are visible for all cameras, so we can send all those all these sub-point cloud to the model. On the green, the second and the fourth one, they're not visible, so we don't need to send them. And likewise, on the yellow one, only the first and the third one are not visible, so we don't need also to send them. So in our experience, again, we use the encoding context. So we evaluate of the 110 images of the dataset. And we have two abbreviations here, which is one the lossless encoding in terms of geometry, and the other one is loss encoded. So here first the sampling. So the sampling we can notice that first there's a significant increase in quality when you increase the resolution from 9 to 10, but not to 10 to 11. And if you take into account the number of points and the quality metrics, the Poisson disk sampling with the resolution of 10 seem to have the optimal combination of both. And that's what we use for our pipeline to generate point clouds. So the experience in rendering quality, we have evaluation of the training views. So we can see here first in the average where the types of PPC, they rendering with the Plenoptic point clouds, they outperform the vanilla 3D.js by about 1.5 dB. And that's because a certain specular scenes, they have a bigger advantage because they can model the specular highlights better than the vanilla implicit approach. But however, these model sizes they are fairly different. So because the model sizes of the original Plenoptic point cloud is too large, we also do a compression efficient experiment where we take into account also the size. So here on the table, the first solution here is our first contribution. We do the predictive compression with the Plenoptic point clouds. The second one here is the occlusion aware scheme that we propose here. The third one is the visibility pruning that we proposed. And we use our second contribution with the doctrines as the anchor. So here you can see as the third proposal has a averaged out performance, the Plenoptic point clouds, even for occlusion step. Because of average rendering quality. But for certain specular scenes, again, the occlusion aware approach with the Plenoptic point clouds outperforms the implicit methods. So you can see one of these plots. So this is one of the specular scenes. Here you can see in blue is our first contribution. The second contribution is purple. The third contribution is in green. And you can see how the occlusion is the light blue outperforms for the specular scenes because of this better highlight representation. So just to visualize, here you have the comparison of the ground truth with 3D.js. You can see how the highlights are a bit smoother. So it has almost a 5 dB decrease when compared to the uncompressed point clouds. So the models are better, but they also, in terms of rendering quality, but they're also much bigger. So you can see the solution was 80 megabytes, but the Plenoptic point clouds more than 800. So after we compress them, we still are able to outperform in terms of rendering quality, but we also have a size that is now smaller. So in short, we're able to propose this approach to assess these explicit and implicit representations. So we generate, in order to that, we need to generate the Plenoptic point cloud systematically, and also propose this encoding scheme using the occlusions to better encode these models. So these benchmarks for rendering quality suggest that the PPCs, when not regarding the size, they outperform the implicit representations. But because of the differences in sizes, when you compress them, our scheme, the direct contribution, presents a BD PSNR gain over our proposed Plenoptic point cloud scheme. So to summarize our contributions, first one, we propose this Plenoptic enhancement on the explicit side using the GPCC coding strategy. Our second contribution, we move to the implicit paradigm. So we propose the comparison of Plenoptries while maintaining the rendering quality and speed. Our third one, we propose this flexible pruning implementation for radius fields. So we can use this underlying geometry to prune the elements. And the fourth one, we summarize by providing a equal comparison baseline between both approaches. So we do that by having these 2D base metrics. So we do the final images, so we can compute with that the PSNR, the SSIM, and the learning based also the LPIPS. And those show that the scheme tree provide the best results in terms of BD PSNR. So in terms of perspectives, our first one is that 3D.js still presents room for improvements. So if one follows the field of novel synthesis, one can see that a lot of solutions are proposed for in every conference, normally more than 50 for each one. And so the first one, the first approach that we can use to improve it is to improve the representation, because the spherical harmonics that it uses is often considered because of future previous works, almost like a legacy kind of implementation. So we can also reduce in terms of compaction by reducing the number of kernels, but also providing more compression, more efficient compression of the splitting parameters, and so the Gaussian parameters and the spherical harmonic coefficients. And also a discussion that has started is if you want to have a sparse model and you want to control its densification when you create the model, or if you have a dense model and you want to control the pruning. So there are arguments of both sides. For the pruning, you can have a more controlled reduction because you already have a more complete model, so you can kind of guide while you're reducing. And is really just the future of the Plenoptic senior presentation. And it's a hard question, it's a hard hitting question, I would say, because it's a fast evolving field. It's a solution that appeared 2 years ago. Maybe if somebody asked me 3 years ago, I'd say the Nerf maybe is the future. And but the fact that MPEG starting standardization activities bodes well in terms of a long-term perspective, because it allows standard use of these applications. So the future, I would say this merge of these explicit and implicit representations may be the future. So as you did in the second contribution, where we merge classical explicit techniques for these implicit methods, that could be the approach to move forward. So these are the contributions associated with this work. And we also had a fifth contribution that we don't explain here, but because it was as a data set paper that we provided contributions in the collection, the processing, and the analysis of the sequences. And it was a bit out of scope of the presentation of the story. So thank you.
Thank you very much. The class was really timely. So now we will go for the questions, and I will first start with the reviewers of the thesis. And first with Professor Adrian Munteanu, who is online.
Yes, I'm online. I just was looking at the camera. It seems to not let me start. Just a second. Okay, now it's fine. Okay. First of all, congratulations for this nice amount of work and publications. Also for the nice presentation, which is really summarizing very well your contributions. I would like to ask a few technical questions. Honestly, I've been in Rennes PhD defenses before. I don't know whether the procedure stays the same. Also, it's a double degree, so I don't know. I guess you are following the rules in Rennes, yes. Meaning I have like 15 minutes to ask questions, right?
Yes, the first question is yes, that's the French procedure.
Okay.
Process, but
yes.
The limitation to 15 minutes is not mandatory.
Okay.
In theory, you can ask how many questions as you want, but of course.
But we are many reviewers here, so we have to be reasonable. Apologies for not being able to be there. I had to teach today. I would have liked to be there on site. I see the room is nice and full. Gautier is, I guess, is over there on site, so at least you have someone there. First of all, in page 40, and actually conceptually, you are proposing, page 40 of the thesis, you are proposing the rough transform with the KLT, and it systematically improves, adding the KLT systematically improves performance. The logic I find there is that basically RAT doesn't do a good job. And first of all, remind me, please, what's the delta between adding the KLT and not adding it?
Mhm.
Secondly, yeah, KLT is one of the possible solutions to further decorrelate. Did you try to consider other ways to further improve performance, other alternatives or not? Feel free to comment.
So the first question regarding the usage of the KLT. So the KLT, when you compare it to just using the color attributes, the KLT allows us to prioritize the information into the first main components. So it's a bit of an energy compaction when you compare to the only the conventional colors. So when you use the upside down rats, which has a predictive type of information instead of just the conventional rats, it allows us to encode the residuals rather than the colors themselves. So we apply the residuals rather than the high and the low frequency components. So regarding the different transformations, we did some experiments also with the DCT. So we
Yes.
had different types of DCT, and also we have different types of scaling. So we can have a uniform scaling of the ACs, and so we use the one that proved to be the most efficient for us, because the KLT at the end is kind of like the asymptotic.
But complexity-wise, how fast is it? I mean,
Yeah, that's something that I didn't really put exact information in the thesis. And it's a good question, because I would say it's probably the main drawback is first because you need to encode multiple attributes, but it's more related to the representation rather than the method, because the representation, since it has multiple attributes, you need to encode each
but then
attribute.
related to that, should you correlate the same, transform the attributes, or should you maybe better specialize and go on specific attributes with specific transforms? Did you try any of that?
Yeah, so when we have the comparative assessment, when you encode the sub point clouds rather than the full point cloud with transform coefficients, we in fact to have a certain speed up, because we send to encode fewer points. So we still have more or less the same amount of cameras, because they're not transformed, but because you only send the non-occluded points, we have these smaller subbands. So although we do different point clouds rather than one point cloud with multiple attributes, we have a certain acceleration because of that.
I see. Did you try to do, I didn't see it in the thesis, or maybe I overlooked it. Did you try to do a sort of ray distortion optimization, ray distortion complexity optimization? Sorry for that. So basically, take the rate and some sort of constraint on complexity and say, give me for that the best.
No, we didn't do that. We only used the combination of attributes that are conventionally used in the common test conditions of the PCC.
Yeah. So basically, you didn't try to do rate allocation essentially.
Yeah.
Do you think we should go in that direction?
If you go into the explicit side, I think it's probably the way to go. Most of the solutions, because if you take into account the solutions for the implicit methods, like the 3DGS, for example, most of the new compression methods, they use some kind of bit rate allocation in the loss function. So,
yeah. But that's at training time. But I'm speaking at a runtime. Suppose that you have a variable bandwidth on a communication channel. You have your very fancy representation stored somewhere in the cloud, and you want to serve several terminals with several capabilities. You also have latency constraints. Suppose that you are using these immersive representations to be able to navigate in virtual environments. So I wonder, how do you take that into account? The latency, complexity on the decoding platform, do you do the rendering in the cloud, do the rendering on the terminal, maybe express some opinions. There are many questions, so maybe take them one by one.
So first, the way to do it, I would say, is probably use the lambda on the rates and distortion to control either one of the parameters. So if you want a certain rate, a certain rate distortion, so then you can just change. Regarding the approach on the cloud or on the locally, I would say That's a good question because I think it also depends on the kind of application. Say, for example, if you...
Imagine a concert going live, and then you have this big machinery computing your representations live. And the compression is also live, well, live with some decent delay, let's call it that, right?
Yeah.
And then you want to serve your clients, but then each one has its own bandwidth. How would you do that?
I would probably assume they have a kind of like a cloud kind of structure, and then you can use the bands to kind of like automatize this kind of allocation. But, so I would probably input into the cloud rather than the local.
Okay, but I guess you will need a sort of ray distortion optimization technique running in the background to tell you where to cut, which information to send and which one not to send.
Yes.
Also, you dedicate a lot of efforts to visibility, and you're using visibility to actually drive your compression process and efficientize it, really improve performance. Now, visibility depends on the viewpoint, and suppose that the users have different viewpoints. How would you handle that aspect? What to serve to each?
Since you use the training data, it depends of the data set that are used, so the scene that are used. So here, since these models they're trained per scene, we need some kind of training to have this kind of approach so we can do the number synthesis. So normally compute this during training. So what is gonna adjust depending on the data set, the data that we have, is that the training time could be longer or shorter depending on the scene. So here we actually have there was an extension that we did for this visibility pruning paper, and we also tested with real world scenes. So just to give you an example, like the drum data set is a synthetic one. It has about 300,000 points, 300 Gaussian kernels. And when we apply our scene, increases the training time from 9 to approximately 11 minutes on a A40 GPU. But when we have this large scale scene, which I think is around 5.7 million Gaussian kernels, that's the biggest drawback. It increases the time from 15 minutes to just 3 hours. But the good thing about it, however, is that the inference time, there's a speed up with that. Because since you are reducing the number of points, when we compare with the vanilla version, we can have outperformance in terms of frames per second. So with the vanilla 3DGS, for example, this large scale scene, it's about 45 FPS for the vanilla model. And just applying your visibility pruning, you already can almost double the performance.
No, that's clear. But my question was in fact on how do you address different viewpoints from different users willing to consume the data from different viewpoints? So basically, you have to encode at runtime what you serve each one, right, or not?
So the thing about encoding runtime, there's this problem that is the underlying representation, because since it has to encode per scene, all these models do have this kind of let's say heading time. So even if I have a quick training times, for example, for smaller models have like around 10 minutes, but all these vanilla models they have this kind of constraint also.
Okay, I understand. But then let me go to a conceptual question. You traversed nerves. You also, I mean, you worked on nerves. You also worked on combined representations on 3DGS. As you mentioned at the end, there are activities in MPEG going towards 3DGS representations for dynamic scenery. And I was wondering, how do you plan to adjust or modify your methods in that context?
There have been some solutions with both the nerve-based models, with the 3GS models, to create methods that are generalizable, so we don't need to encode for each scene. So in the context of MPEG, I have been following that in close in terms of if they plan to apply this kind of methods, so we don't need to have this encoding problem for each scene, so we just need like the decoding. So I would assume that that's something that they have to address, because otherwise you need this encoding time, so it kind of detracts from the whole real-time rendering. That is an advantage. So I would assume.
But would you favor NAS and
Between Nerf and 3D
yes, for dynamic scenery?
for the dynamic scenes, I would assume 3D because since it has a bit of localization, when you have this time domain also, this localization makes it easier to transition from frame to frame. So if you do like an intercompression, it's a bit closer to how the explicit methods do, and there's already a lot of work put into that. So since Nerf has this kind of encoded geometry on the neural network, you need to account to that also.
And how would you do temporal prediction of your, let's say, quantity structures?
Of archery structures?
Yes. Yes.
Quadrips. Okay. There was original work, I think it was 2 years ago, which it's called Fourier Plenoptic. So they encode the time with the using a Fourier transform. So they transform into the time domain. So,
okay, so you do that. You go in the transform domain and open it there.
Yeah.
Okay. Do you plan contributions in MPEG in that? Because there are activities going now.
Yeah, so with the, as I said, I haven't been following closely what's the activities that I do. So I can't say exactly for sure if it's something that I'm interested in having an exploratory experience about it. So it's something that I'll have to dive a little bit after this whole process.
Okay, so it's yet to be seen. I have
Yeah, yeah, it's a good question. I tried to talk a little bit about it in the updated version of the thesis. So what we assume is how the LOD is generated with the residuals because of the neighbors that they use to generate the predictions. When you use attributes with because you're not using the colors anymore, you're using especially on the AC side, because the DC still performs fairly even when compared to the main attribute color, so like the RGB. But the ACs, especially like the lower ones, the lower values, they start to deviate a little bit on the matter with the LOD generation. So it's a matter of the values being lower. I think there's a bit of a quantization problem on the LOD side. That's zeroing points of making as they're closer to zero. Then they deviate.
So it's all in all, it turns out that even if transform is better, actually in the end you don't gain. In that particular case, is that so?
If we took only the DC, they still have.
Okay. Then it will be fine. But you also take the ACs and you pay.
Exactly. So the ACs are the bigger difference on the metrics. We actually have a small table kind of showing like the first DC and the first and the two ACs. So here we're pretty much using the LOD as the anchor for the DPSNR and compare the red. So you can see here on the, I can show the pointer here on the screen so you can see.
I only see the slides. Okay,
so here we compare the main RGB. So the red base actually loses by slightly for the PSNR. And when you take like the overall, like all the colors, it gains by about 0.5. So when we split into the DCs and the ACs, this thing then starts to grow and increase.
I see. Okay, great. Maybe I have one last question, and then we move to other reviewers of your thesis. So I see that the PSNRs move around 30 to 33 dBs. Honestly, if it was for pure classical image compression, that would be in the low range. Maybe can you comment on that? How can we go towards higher PSNR values?
Yes.
I mean, 37, 38 to 40, that's one. And secondly, in one of the experiments, I saw that actually you can pay only 0.08 dBs, and then you get half of the Gaussians down. Can you comment on actually how to find a good trade-off between how many Gaussians to use and rendering quality?
So first, regarding the quality metrics, I'll refer again to one of the extensions that we did. So we did also an extension for the comparative assessment. So we compared the Plenoptic point clouds and the implicit methods. So I do compare with slightly newer state-of-the-art solutions, because as I said, CISA is a very fast evolving field. The state-of-the-art that when we first published the paper was already pretty much different from now. And even 2 months ago was already pretty different from now. And,
I know.
so we compared the 3DGS and 3DGS version that is for reflections. So they have a kind of a parameterization to better represent reflections. And we compare with the Plenoptic point clouds at the end. So if you have models that they have reflections, but they have a simple geometry and a simple texture, the 3DGS and its corresponding reflective solution, they can increase the PSNR by almost 50 dB. So here, the Plenoptic point clouds, in fact, they lose, even though they normally outperform in specular scenes.
Yeah.
So because it has a simple geometry, a simple attribute, you can modulate this with the ellipsoids in the format, and you can modulate it with the spherical harmonics, the colors.
Yes.
When you get to more advanced either geometry or the...
Then it's finished.
Yeah, so then you can see how it has trouble to reach. For the vanilla 3DGS, it has trouble to reach even 30 dB. And for this new solution, at the time when we did the extension, was the state of the art, the HAC++. It outperforms by almost 4 to 5 dB, the vanilla 3DGS, even though it has a compression pipeline in it. But we are able to outperform with the PPCs. So the thing is, if you compare this new solution and the PPCs, the new solution is actually pretty close in terms of the state of the art. But at the time when we started, it was, if you just compare like the B, which was the state of the art doing
it was far away.
It was far away. So I just say
now, still 32 dBs. We all agree that these nice specularities are being rendered here, and even if it's only 32 dBs, it looks good. I was wondering just going higher, if it's that anyway possible in the future. But maybe I let my colleagues further discuss with you on that. I really like to thank you for your presentation. If there is a second round of questions, I will also have a couple of more questions. Thank you for your answers.
Thank you for the questions.
Thank you very much, Adrien. So now we will go for the second review with Professor Gauthier.
So first of all, I have to congratulate you about the manuscript. I like the structure. But there's something that a philosophical question, let's put it that way. Perhaps you should go to slide 87. So that people can follow.
Okay.
So actually, you speak about nerve, which is implicit, right?
Mm-hmm.
You speak about 3DGS, which is explicit.
Yeah.
That's explicit.
Mm-hmm.
That's you have the points in space, so to me it's explicit.
Yeah.
But then, and I saw that in your manuscript, and I have the same impression now during your presentation. The Plenop trees, you call that what? Implicit, I have the impression.
So that's a discussion that every conference that I participated, we've had with the people there. So we call it explicit radiance fields, but so it depends a bit of the perspective where we come from. So if we come from the perspective of the radiance fields, so if you compare like the vanilla nerve, where it has like completely implicitly, we call them like both the Plenoptries and the 3DGS as explicit radiance fields. But here we define the implicit representations as being implicit with the continuous functions either on the geometry or the attributes. So since here we have these attributes being represented by the spherical harmonics coefficients and the here on the 3DGS, you also have the parameters of the Gaussian kernels and the opacity, so you can blend them. We call them implicit because of that to differentiate to the full explicit methods.
Okay, well, to me, explicit means that you have really a geometrical representation, and implicit is you don't have the geometrical representation. So to me, nerve is totally implicit. You have the full representation somehow in the weights of your neural network. But when I look to the way you do plenoptries, you start with a kind of nerve thing, and then you say, after the nerve portion, the training portion, you come with an O3 representation, which to me becomes explicit. And the compression you do is with GPCC, which is also explicit. So I would rather say that, especially from the compression point of view, and that's what you say here in slide 7, and that was the thing that made me a little bit tilt. To me, the compression that you have done is always GPCC in that nerve plenoptries-like stuff. So it has never been an implicit compression. Implicit would mean that you take the nerve neural network and that you compress the weights.
Yes.
And that, did you try that or?
No, so what we wanted to do here is to kind of like combine. So we do like we leverage these explicit approaches, these explicit methods, but we do compress the geometry because we have the positions on the O3. But the attributes, they have some kind of information of the geometry too, because the density information, you need that to if the corresponding points that you render to have a final geometry. So if you take just the whole space and ignore the density values and the spherical harmonics, so just take the geometry, so the positions of the voxels, it does not give exactly the point cloud geometry that you envision, because of this blending information that you need for the density. And the 3DGS also has this blending aspect, because since it's a bit of it's not based, but it's close related to the steer mixer experts. But those that use the gating functions to kind of fit the Gaussian kernels, here into the DGS use the opacity values, so they can kind of do the blending also as the doing nerve. So the opacity value, there's some information on geometry depending on the view, because you have to accumulate those views to have the contribution of the color for the pixel. So that's why this distinction.
Okay. And can you say something about the bit rates? Because when I look to all your slides, sometimes I see even 30 gigabits per second or 30 gigabyte. I don't know for sure. Sometimes it's gigabyte, sometimes it's even megabytes.
Yeah.
There was one slide where you had, I think, slide 44, where you see the full range. And depending on the solution that you had, you were more in the gigabytes or gigabit per second, I don't know. Yeah, here.
Yeah, here on the compression of the second contribution, we use the GB-bytes. Yeah.
So this is a static scene. The label is static.
Yeah, it's a static scene.
So the baseline plenoptries is gigabytes. And then you have a solution.
Sorry, this is just the label. I think the label is a bit deceiving. So it does not mean that it's 1.4 gigabytes. It's just the compression that they produce. It's called that. So, but the sizes they are in the same unit for all of them.
Yeah, but I'm not looking to the red box. I'm looking to the horizontal axis.
Okay.
There you have 10 to the power 0. I guess the 1.4 gigabytes is more for the spherical harmonics.
Yeah.
Probably.
Yeah.
So here I see full range, and I see that you have RAD is really at the low range of gigabytes. So you have 10 minus 2 gigabytes. so in the tens of megabytes. So to me, it looks to be a very good solution to have RAD and GPCC is the same, so to speak. So I'm a little bit wondering, why would we go to other solutions, also looking to the Gaussian splats that are basically, what would be your recommendation, and especially for dynamic scenes, of course?
I would say I'm a bit biased towards the coding directly into 3D space, so GPCC in that case, because what I noticed when we try to do any type of lossy compression in terms of geometry, we also have to take into account that the attributes related to the geometry, they are going to be used in the render view, and this is going to be accumulated. So small errors in the geometry, for example, with the tri-soup, even the new version of the tri-soup that was very effective in terms of lossy encoding of the geometry for point clouds. When we try to apply them for this kind of implicit representations, it was creating like a snowball effect, and the results were becoming much worse because of that. So I think I even like a plots on the comparison paper. So we use the new tri-soup from this geometry solid model. When we get there, you have to skip the animations.
But so you would recommend to go to continue with GPCC?
Yes,
and knowing that for dynamic things it's difficult, and also if your scene is changing, the whole tree balance is also completely changing. I'm not so sure that for especially the dynamic extension, GPCC is the good path to go. I'm biased to the 2D video.
Yeah, it's a good question. It's a good question because, as I say, we have these two different, let's say, problems that we have to address. So indeed, the VPCC is very powerful when you have dynamic sequences. But I haven't been following that close the latest evolution solutions on the GSTM from the GPCC code standard. But I think they have some new explorative experiments on the inter-prediction that I think it's reaching a pretty competitive stage in terms of dynamic sequences. But I haven't been working on it, so I can't say for sure because I haven't seen, I haven't done the benchmarks myself also. The benchmarks is not comparing them directly.
Okay. And then a last question about the number of Gaussians. I think you had a slide where you really reduce the number of Gaussians.
Yes.
I really have the impression sometimes that to go forward in a good compression, you should rather be very careful about where to put your Gaussians and have a quite sparse distribution of Gaussians and that it does not change too much in time, rather than trying to fine-tune the codecs, whatever codec it is, GPCC or 2D video. Really put all your effort in the pre-processing to have good distribution of Gaussians. Is that correct?
Definitely, I'm completely in accordance. And this was one of the main challenges that we had when we started working with Plenoptics, is because since it stems from the NERF model, which doesn't have really a concern for being sparse, because well, the geometry is encoded in the neural network in the weights. The problem is that if you have some information that you can't really represent just with the RGB triplets, so just with the density, it has a tendency to over-parameterize. So, for example, the image that I showed with the bucket, so when you compare on the B, you compare like the whole, which looks less sharp on the vanilla version, and ours it looks a bit sharper, and we prune, and we still have some kind of advantage on that frame, is because at this point they are not helping on that frame, but they are probably being used to interpolate for another frame. So if you have, for example, if you have a certain model with a few amount of points, NERF, like the original NERF, if you just extract the points, you create a bit of a a thickness, a carcass over the original model because it tries to represent the some light information, for example, reflections, transparencies, by adding more and more points. So the 3D Jazz House has this tendency too. So that's why it has this increased number of Gaussians. So you can reduce some of these Gaussians and still have a similar metric because they are not supposed to be there when you compare it to the original geometry.
And do you have some ideas about pre-processing to get rid of these nasty Gaussians?
So that comes at the discussion that I mentioned about should we come from the dense model and start pruning because you have a more complete representation, so maybe we can model the pruning, or should we come from a sparse model and then control the densification? And honestly, I can see arguments for both. Me personally, since I worked already with the pruning method, I think I'm probably biased and say, okay, so maybe we could improve the pruning even more. But as you show in the plots of the number of Gaussians, the method in the state of the art, which is the here, it does exactly that. So it has a dense model, then starts the pruning during the training. Once it stops dividing and splitting. Us, we try to control during the training, so it doesn't reach, let's say, a very dense model. So it makes it a bit easier for us to prune because we're pruning during the densification. So we embed during the training, and the results they seem to be favorable to how we did it. So although we are pruning from a dense model, the way that we did it closely resembles the way of controlling the density first, and then maybe doing some extra cleaning of the geometry. Let's say.
Okay, thanks. Very good. Thanks.
Thank you. So now we'll go to the examiner and we'll start with Professor Mylène Fargas.
Okay. Yes. Thank you. So first of all, I'd like to say, Davi, that I enjoyed a lot reading your document. It's really looking good. I did find a couple of typos, but they're always there, right? So I'll send you a couple of reminders later. So I'm going to focus, since I have like a couple of minutes, I'm going to focus on one aspect that I found interesting is the following. So over all your works, of course, there is one thing that caught my eye because I'm from image quality, is the fact that you use like you measure the performance metrics in different ways. You use, of course, the sorry, let me just take a look so that I say it correctly. So of course you use the BD graphs, and you also use a couple, when you could, I noticed that you use 3 basic image quality metrics, which I am supposing that you took from. And the metrics that you use were PSNR, SSIM, and LIPS, if I'm not forgetting. Sometimes I confuse the name very much. But what is striking me, and I would love to hear your answer, in the sense that you played with these metrics, we played with this algorithm. And so for the overall algorithm, what I noticed, especially for I would say the last ones, is that the metrics didn't quite agree. So especially like leaps, some of course I'm saying they agree more, but I was wondering if from you that had played with the signals and saw the different, if you had a feeling about this, and even if you think that maybe there could be another metric that had maybe a better.
Yeah, so first, in terms of the metrics, we wanted to use different ones because since there are so many new solutions, it's a bit hard to just say, okay, we're outperforming one, so it's better. Especially because the first few models, the Nerf, the Noctis, they are trained and they are optimized over the rendering loss, so the rendering the MSC based loss. So the PSNR is bound to outperform in that sense. The loss function of 3DGS already targets a bit into that by, I think I have the loss function here. It already targets a little bit into that by, in addition to have
Using-
this MSC based loss, also use a SSIM based. And so that already makes a bit closer to make it easier to agree, both of them. And the LPIPS, as you said, they normally follow them because especially for the 3DGS. For some nerve solutions, especially for compression, the LPIPS didn't always agree. So some models they lost in terms of personnel and SSIM, but they won in terms of LPIPS. And the biggest challenge that we had when doing the framework for the Plenoptic point clouds was indeed how could we compare these explicit methods with the implicit ones. Because as you know, the Plenoptic point clouds they normally use maybe D1 base metric for the geometry, or maybe a PSNR over the color channels of the attributes, so directly into 3D space. And the methods of the implicit, they normally use these render views. So what I wanted to do is kind of like to have like a approach that's, I wouldn't say fair, but it's mostly easier for the community to understand, is to try to compare them over the same metrics. And I think for the evolution of new solutions, I think understanding that these two communities have to merge, and for that I have to compare those. I think it's important to have metrics that both sides understand. And so, like our proposal, I think it's a good way to, obviously biased by saying it's a good way to approach that. But I think we did at least a decent work in trying to, well, how do they assess, like in which, let's say, scale they compare.
But do you, when the leaps performed better visually, what did you think? Because I think you answered some of this in the text, but it was only for one particular scene. I was wondering if when you saw several scenes, what did you think? Who do you think was had was real feeling, especially for the end one,
Yeah, that's a good question. The first thing that caught my attention is that when, for example, we have some blocks. For example, one of the extensions that we did when you work with the implicit scene, implicit quote unquote, because it's the 3DGS. But let me get to the. It's a bit behind. So we did experiments with different values of the MV parameter. So here the PSNR dropped quite significantly because of the background. But I didn't put it here, but the LPIPS, it took, it only broke after the foreground also kind of broke, let's put it that way. So I think there's a bit of a region of interest aspect that the LPIPS takes into account that I think it's important also to evaluate. But since
and I
it's
know
not
that
as
I'm pushing you because in a way, the only way you could answer that if you, which is not your genius, would have done an experiment and would have compared. But so I'm just picking your brain since you played with so many of this. Yeah. So the other thing that I was curious was the following. So I like that you played with three metrics. I think it's great because then you get these problems and it looks to me that you might even have a couple of data there that you didn't explore. And of course, I'm curious because I'm from the area of quality. But one thing that I noticed is that for the BD rates, you only use the one with PSNR. And I've seen even like MPEG and JPEG, they're going foreign using maybe VMAP, maybe also the BD for with VMAP and even SSIM. And maybe you just didn't include. But if you had traces, sometimes like traces you kind of plot everyone and they're all the same. So you think, why is it? So I was wondering if you had the opportunity to plot them in different metrics.
In fact, we did explore different metrics in terms of the geometric line metrics. So we computed also the bit rate just to see how it compares. We know it every because the term of the distortion is still the same. You see the JSON-R.
Okay.
But in short, yeah, we didn't explore these other metrics.
Okay, I see. No, very good. Yeah, so can I pick, so for this very last proposal that you proposing with the two graphs, I don't know if maybe you can come back with the two graphs in the end. So I have not been very specific.
This one?
No, I was thinking of the very beginning of your last chapter where you have the explicit and implicit and you have, yes, that's the one.
Okay.
So I'm feeling, so you didn't present a lot of, you did present a lot of complexity in terms of parameters, but I was also curious about the runtime and the heaviness, the complexity of the models more in terms of the training and everything else.
Mm-hmm.
I was wondering if you could, from these two, you could kind of list me, tell me what was your experience in terms of the complexity. Not only the complexity, I know that they're related and you could try, but but if you could tell me a little bit of what were your numbers and how much were they taken, and I mean, being connected. Is this something, are we close to this? One thing that I found with the radiance field is that they're so specific to one scene that sometimes I find it difficult.
So in terms of running time, sorry, I think it's a good question because it's exactly one of the, I'll say, the drawbacks of the Plenoptic point cloud is because in terms of scalability. So when you have in case you have like the encoding of the scenes, if you have for example, if you take the 8i data set of the point clouds, they only have the 12 or 13 RGB triplets. But the point clouds that we created here, to make it fit to the conventional data sets that we use, they have 100. So we need to encode all of these colors, all these attributes. So it doesn't increase linearly, but it's pretty close to linear. So if a point cloud, for example, with 300,000 points, so which was more or less what we had for example, this scene of the drums. With the 100 views, it take the encoding about 15 to 20 minutes. Here on the 3D.js side, we can have encoding the training for about 9 to 10 minutes, depending on the GPU. So, but as you increase either the number of points or the number of cameras, for example, the real world data sets that we use, they are considerably larger. So they about 5 million points, but they have more than 200 cameras since they're large scale scenes. So the models of the nerve type, they increase to about 45 minutes. The PPCs, we're not even able to run them because it was too cost intensive in terms of resources that we had. So the point clouds themselves they're being so large that it's a bit hard to do a comparison because it take a lot of time both in space resources but also in computing time.
Yeah, I was just curious because there has been some proposals that are lighter, right? And done for consumers to capture on their phones and use it. But my experience with it is that the quality is not even close, So that's what I was very curious. I don't want to. I'm a little bit lost on the time, but there is one other thing that I was going to ask you. When you did, the performance metrics and everything, every one of them was based on luminance only, right?
Yes.
Do you think that, for example, maybe adding color and it would, have, even like in the loss matrix, maybe if we had some kind of color measurement, would this make a difference?
Yeah, I'm glad that you asked this question actually, because one of the extensions that we did for the comparison, we had these plots where we took the luminosity and also the chrominance values for the Plenoptic point cloud that we created. So now get there. So here on the left we have the synthetic data. On the right we have the shiny data, so it's also synthetic, but they have more reflections. So when you take only the RGB, I didn't put it here, but the RGBs, they are closely at the same level.
Okay.
But when we convert to the luminance and also the chrominance, you can see as the variation. So here's the variance between the color channels of the plots of the plots. So we take the variance between the color channels, since you have one color per camera, and then we apply the average for the whole point color. So the values
looks like
that are
luminance
mostly
is
concentrated.
capturing quite well.
Yeah. So they're mostly concentrated in luminance.
That's very interesting.
So the specular increases, you get a much greater increase in the luminance also.
Yeah, it's very interesting. It does show that it's capturing a lot. Okay, I think I'll let the other reviewer talk. And thank you so much. And I really did enjoy your thesis and the presentation. Thank you.
Thank you very much. I will now go to the second examiner with Professor Marc Antonini.
Okay, can you hear me? Can you see me?
Yes, very well.
Okay. Thank you. So I want just first to apologize for not being able to attend today due to professional commitments. So for the PhD presentation, it was very nice, a very clear presentation, very dense presentation. I think a lot of work has been done. I'm not familiar with all the things that you presented on the radiance field or plenoptic point cloud. So probably I will have some high-level question. And my first question is about the benchmark and about what are the limitations of the current benchmark when comparing explicit and implicit 3D scene representations in terms of compression and rendering quality.
So the first challenge we noticed when we wanted to provide this kind of comparison was that the metrics, they had a different, let's say, purposes. The explicit ones, they are generally more into the 3D space, so they are normally directed into maybe a point-to-point metric or point-to-normal metric, so they have the surfaces for the geometry. And also for the colors, they use the color channels for the points directly. And the implicit ones, a lot of times they don't have even a specific geometry, so we can really do this kind of comparison to this space. So what we did on this comparison paper was to attempt to closely relate it both by approximating the explicit ones into the implicit ones. So since we can do this projection from 3D to 2D, we attempted to give these metrics on the explicit side, so we can evaluate over the same set of images that you can generate for both of them. And then you can use the conventional 2D metrics. As we were discussing the PSNR, the SSM,
Yes, and it was one of my questions. One of the questions of Milan was one of my questions about quality assessment of the 3D data that you are producing. So if I understand well, you are projecting on the 2D space and evaluate the quality on the 2D projection of your information. And this is true that this is 3D information, so it contains geometry information. And I guess it will be interesting to check a 3D distance directly on the reconstructed object, such like outdoor distance or things like that. What do you think?
I think so, but the thing with that is that we need some kind of the ground truth um, geometry to compare to. So for example here, uh, since the original models that they use, for example, for the synthetic data, they are meshes, uh, we sample them and use the sampled models as ground truth. However, the challenge is that can one say that is it the ground truth if you're already sampling from the meshes? And so since you're the ones creating the data set, I guess okay, we can create this ground truth. But if the models are not properly sampled, you can cause issues, not because of the colors you generated after, but because you sampled the geometry not optimized. So we create a bit of a asymptotic, we create a ceiling on our performance because the geometry is not properly sampled.
Okay, understand. And when you are optimizing your codec, you are minimizing mean squared error, I guess, or in the luminance domain, or are you combining chrominance also?
In the codec, you mean on the explicit or on the implicit side?
On the in the explicit side.
In the explicit side, we use on luminance.
Sorry,
On the
you use?
explicit side, we use only luminance, so we use the wide
Okay.
space.
Okay. And did you try to optimize a trade-off between, for example, luminance MSE and SSIM, as it is done, for example, in JBI?
No.
Try to take into consideration some psychovisual information in your optimization, because I'm not okay. PKSNR, all your evaluation is done in PKSNR, but there are a lot of criteria for estimating image quality, and probably I don't know what is used in MPEG, for example, but I know that in JPEG we are using several criteria for evaluating quality, for the evaluation of the quality, and so if you have any argument on that, or to explain why only PKSNR?
Mm-hmm. No, it wasn't something that we explored. We also had a few constraints of time. So there are some experiments that we wanted to do and we want time to further explore.
And for example, in the standardization, they are using only PKSNR in MPEG?
For the current standards for MPEG, I can't say for sure for 2DJs. But if they're using the same as the vanilla, they're using also the SSIM.
Okay. Okay. And in terms of compression, how do you estimate the highest compression ratio that is acceptable? Okay, I guess that you are doing some kind of psychovisual interpretation of your image.
Mm-hmm.
And when do you say it's no more acceptable and the compression ratio is too high? What kind of criteria are you using, or visual criteria are you using?
Mm-hmm. Yeah, that's a good question. When you talk with the implicit methods, so for the explicit methods, the common test conditions kind of guide us in a way to in terms of okay, so maybe how much distortion should be acceptable. In terms of the implicit ones, it's a bit tricky because as Professor Adrian he observed, the the implicit methods such as you can see these two here, so these ones they're based on 3D they are normally they have like a workable range. That way you compare with the explicit ones, they are a bit limited. At least they're the ones that we explored. So they are able to reduce by decreasing the quality a little, but there's a point where it just like completely breaks. So if you extend this range, so these ranges that we worked were ranges that are proposed in the state of the art. But if extend uh, here on the low side, on the lower bit rates, it reaches a point where it just breaks. So it's not as smooth as a transition. And on the high bitrate size, it saturates. So as it is, if you don't have any kind of information to better densify your points, you can reach high bit rates, but you won't have a higher quality. So yeah, it gives a bit of a saturation in the high bit rates.
And the density of the point that you have is linked to the resolution of your input data?
For the implicit scenes, well, for the 2D Gaussian splitting, there's not a specific resolution. So there is an underlying resolution which is related to the capture devices that you use and the scale of the scene. But the points, the Gaussian kernels, the positions, the pixelized. Here on the explicit models, when we did the sampling, we did test the different resolutions, and we noticed that for the data that we used, a resolution of depth 10, so constraining on the 2 to the power of 10, a little 2 to the power of 10 for each coordinate, it gave a good compromising number of points in quality. Because in terms of when we increased to 11, we increased the number of points a lot, but the quality metrics didn't improve that much. And when we decreased to resolution of 9, the number of points they reduce significantly, but the quality also reduces by quite a bit. So if you use a different kind of data, it may be different. So it's not something that we had time to explore, but it could be something that we could estimate since you have the information of the poses of the cameras and the camera intrinsics. So maybe we could do some estimation based on the voxel size and the resolution of the pixels. So we can have approximately fewer pixels being projected into fewer voxels being projected into the same pixel. Because if you have a pixel that is too small, then it's not gonna have a better separation of the voxels because it's gonna be empty. So it's more prone to create holes rather than create a better resolution for the image.
Okay. Okay, so given the growing diversity of Plenoptic scene representations and the thesis approach of adapting existing standards, what is the potential for future trajectory or compression methods that can efficiently handle this variety? And second question, which will be my last question, do you think that distinct standards will continue to evolve independently for different paradigms, such as explicit versus implicit representation? Or can we have something which is common?
For the first question, I would say, to be sorry, I gotta, because I was going to answer the second question first and I forgot the first. So I'll just answer the second question first and then we can repeat the first. So for the second question, actually, we think, we actually had discussions about it, and instead of separating, we actually think that the goal moving forward is to merge them. So bridging the gap between both sides, so people from both sides can contribute jointly, I think is the goal. We had a couple of solutions that we did, actually towards this kind of approach, and yeah, we think it's the way moving forward.
And in that case, the overall performance of the joint system will be the same as if we consider two separate encoders, or it will decrease, or what is the tendency?
I'm not sure I understand the question. Can you repeat it again?
If you assume that there is only one standard for implicit and explicit representation, the performance of this standard, do you think that the performance of this standard will be the same as if we consider two separate standards, specifically for each representation?
That's a good question. I think it depends how much of the workforce is going to be distributed in each. Because I assume this standardization activity, some companies, they will probably prioritize the applications that they're more keen to evolve. So I would say, like in an ideal world, I would say that it wouldn't make a considerable difference. But with the standard activities, a lot of times politics are involved. So I can say for sure in that sense.
Okay, and my first question was about considering this variety of data. What is the potential future trajectory for compression method that can efficiently handle this variety of scene representation?
If one interprets the 3D Gaussian splitting as a sparse point cloud that uses the Gaussian kernels to have a variable splitting, because the point clouds, when they need to be rendered, you have to, like, the renderer has to assume a certain kind of a form to split these points into the image. So they can be often done with cubes, of points, and even only the pixels. So if you assume that it could be a sparse point cloud with variable splats, that could be the Gaussian kernels. One could even explore different types of splats other than the Gaussian kernels. And then we can have different kind of, let's say, splatting based models using different formats. So I think that's maybe that's the way to move forward.
Okay. Okay, so thank you for your answer. So it's okay for me.
Thank you, Mark. So now I will take the floor for a few questions, but not too many. Let me see. Excuse me. So, well, I had also the same philosophical issue as Gauthier about the implicit representation. Explicit, well, for me, explicit is PhDGS is implicit because you get physical parameters, but well, I'll just keep that. And I have a question about your interview prediction method. Do you make the assumption that the color is constant from one point of view to the other?
In the prediction, you mean the first contribution?
Yes.
Not exactly. So we try to address that by having because here, since we're working with the explicit methods, we know exactly which are the colors by working on the data. So we can use that to, when we do like the transform, if the colors are pretty close related, their energy compaction, they're going to be concentrated on the DC, and then you're going to be conveying the ACs in a very low bit rate because they're going to be close to zero. So it's almost like having only the DC channel, and the ACs are going to be close to zero. So you don't ignore, but you almost pretty much ignore the end of the bit stream.
Okay, because as this representation aim to represent non-Lambertian object, then then if your model assume implicitly that your objects are Lambertian, it's a pity in a way.
Yeah. So in fact, we did some. We attempt to have some backwards compatibility with this type of point clouds that want to have like one color. So if you have a full Lambertian model, you don't even need to use the multi-party retrievers. You just use the RGB main, and then the codec only going to encode the geometry and the RGB main.
Okay.
So there was a challenge. There were when we created these Plenoptic point clouds. We also needed to have this backwards compatibility. We needed to have this RGB main color, and we did that by using the occlusion as a.
Okay, that's a good
as a
reason. Okay.
Yeah.
And also, when you do the visibility pruning, you make an assumption on the training camera relative positioning. So are there some cases where it doesn't work?
I was hoping somebody would ask that. Thank you. So that's a great question. It was something that we needed to explain to the reviewers in the extension for this paper. And that, I'm going to go back to the slide that I was showing to Professor Milani. So in this extension, we extended not from the synthetic data sets, but also extended to real world data. So the synthetic scenes, they all have this disposition, like this inwards facing. So all the cameras, they are focused on one object. So with the real world data, not exactly. So we don't have like 100 views anymore. We have like more than 200. And that means that the occlusions that they're gonna happen, they are not always on the from self-occlusions of the geometry of the objects. It could be just because the camera is not pointing to that certain point. So what happens is that here for the real world data, the large scale scenes, they actually perform better than the indoor scenes. Because with the outdoor scenes, they have this kind of separation for the background, for the foreground, since the scales are much larger. But the indoor scenes, the separation is not as good. So for some scenes where the separation is not as good between the foreground and background, the metrics don't work as well. So here, for example, you can see the foreground, because most of the points that we want to compress are in the foreground. It kind of stays during the pruning, but the background starts to break. So if you just take the PSNL metrics, our metrics just fall down considerably. Even though one could maybe argue that if the foreground is okay, maybe if our region of interest kind of information for the metrics, we could properly show that. And when you take the plots between those, here you can see, so the outdoor scenes, you're actually able to perform fairly well when you compare with the state of the art. But the indoor scenes, this information kind of breaks, especially for one of the methods, because of one of the scenes, it just reduces too many points for the foreground too. Because a lot of times the foreground becomes the background, the background becomes the foreground.
Okay.
So, yeah. So it breaks. So we're talking about almost 2 dB here. So it breaks. So it's not a significant break because it's being averaged by multiple scenes. But it's not as competitive as outdoor scenes.
Okay, thank
So,
you. Maybe just one last question about the database that you built. So I guess it is given publicly to the research community.
Yeah. So in the comparative assessment, since you had to create this Plenoptic point
Yes, and my question about it was well, which are the features in this database that are not the same as a point cloud that would be produced by acquisition?
So the first thing here is that since the models are synthetic, we can control the ground truth. So this is not something that we can do with the real world scenario.
Yes.
So we can.
But is it really comparable? Don't you miss things that?
Indeed, yeah, we do.
Okay.
So we attempt to model the synthetic scenes. Here we just use the synthetic scenes that generally used in the state of the arts, like the conventional works. But we have the flexibility here to maybe model some kind of scenarios where we can replicate what we could use in the real world. So if there are some challenging scenes in the real world, we could maybe replicate that into the synthetic scenario and try to see what happens here. So we can change even the camera parameters, for example. We can change the whole scene disposition, the number of cameras that we want to capture. So there's a lot of flexibility in that sense.
Okay, well, already it's very nice to have a new database with ground truth, as you said.
Yeah, I didn't talk much. Sorry to interrupt, but I didn't talk much about the other data set that we had. But we also proposed a multimodal data set that we used to compare. So it was one of the workshops on the Plenoptic program. So when we were in Finland, we had a very powerful capture rig. They were able to produce point clouds. So we produced, so it was a multi-model data set. So we not only provided RGB images, we also provide light fields and the point clouds and meshes. So this is like one of the activities that we had. So we have different levels of point clouds depending on how we process them. So we try to, since you have like this specular information kind of, I try to put some transparency, some specular information just to see how results in the different models. So some models it captures, mainly the LiDAR only based methods, they're not able to capture some of the reflections. But when we combine that with the stereoscopic information to generate the point clouds, then we are able to represent some of them.
Okay. Thank you very much, and congratulations, I didn't say at the beginning, but for all this work, very interesting and timely.
Thank you very much.
Okay, so now I will give the floor to the advisors, starting by Professor Robert.
Sorry.
Thank you. Okay, maybe a few questions. First of all, very nice presentation. One doesn't have to read the thesis after seeing the presentation. Everything was there. You're talking about compression, so this is the main talk, but during the presentation in particular, I was noticeable that you use the word pruning as often as the word compression.
Yes.
So now, do you consider pruning compression?
I would say compaction.
Compaction.
Because then you could include both the compression and the pruning.
And then the follow-up question is, because you have this nice reduction in the sizes, which is very good. Are those reduction in particular in Gaussian splitting coming because of pruning, or they're coming because of the compression algorithms?
Both. So here, just to give you an example in the performance type of let's say perspective, we compared the vanilla one with us just doing the pruning, and then combining the pruning with the compression. So in the second line here, you can see only with the pruning we are able to increase the frame rate, because the number of points, they are considerably smaller. And when we combine with the compression methods, we can improve even more. So it's not as significant as doubling, but you can still achieve almost a 20 FPS gain in the large scale scenes by adding the compression.
So both have kind of significant, basically both would have significant contribution to the...
Exactly. There's actually in the thesis, it's good because I didn't put in the presentation, so maybe you can read there. But we put up a study there. I didn't include it here because it was already taking too much time. So we did have a study just doing the pruning and also combining the pruning with the compression. So we have like the number of Gaussians, but also the quality metrics there.
Okay, good. And then a second question is actually related to something what Adrian was starting to ask, but I didn't get the answer properly. Now, in many of those cases, you are making these visibility masks.
Yeah.
Now, if I consider a scene from one perspective, I can define occlusions and everything for that scene. But for example, maybe I'm not interested in the stereoscopic vision. Maybe I'm interested in these likely displays, superintuitive displays, which need to render big pixels, so completely less. Yeah. How much does this influence in your method? Because if you optimize the scene from one side, what will be the quality when I move 1 meter and so now render me the scene from this side? Or you have to do the optimization? It
makes a very big difference. Yeah. Because when you see the nerf type of models, they normally have these different data sets that either they're inwards facing, they say, or they're forward facing. So the forward facing, they are closely related to the light field type of information. So they normally do a different parameterization to the nerf models. There are some works in the team that use this type of light field information to use with nerf. So I would say, because of this type of foreground and background, I would assume like this type of visibility pruning would break similarly to when I showed the indoor scenes. I would assume it would break similarly in that sense. So we have to do a different maybe type of parameterization to take into account, so we can improve the pruning in that sense.
So you would think that maybe different representation could be needed in general, maybe something beyond this normal Gaussian splitting or beyond the normal lines?
I'd say maybe parameterizing the centroids. There's been some works that they reparameterize the centroids of the Gaussians, so they have like this clear foreground and background separation. But I didn't have time to explore to see if it could make a significant difference. But from the results that we've seen, I would infer I think I would imagine that improve.
Okay, thank you, because this is maybe in the further future interesting kind of IBC to do more wider rendering, since nowadays
Yes.
people still don't want to wear glasses all the time.
Yes.
Okay, I think that there was going to talk now, so maybe we continue to the next.
Okay, thank you. Professor Johan Thanos.
Thank you. So, first, word of appreciation for Davi that it went far back, 3-4 years when we started to work together. We had in common at that time geometry encoding for point clouds. We had some paper with Ricardo back in Brazil. I was working in Tampere with that. So I saw that what we are going to do really will be just geometry. And finally, it ended up here. And I say that I guess we did geometry here. Because what's the difficult part when you have this multi-view from the Plenoptic environment, you cannot make correspondence from one image to another to the points because they are Plenoptic, they are different colors. So it's very difficult. And these guys, the NERF and the 3D GS, they come with some interpolation tools which mash around everything and finally get very good test reproductions. But the question is there the geometry really doing the best it can in this model? If you look at the NERF Plenoptic, they use this density. And we thought first when we tried to compress that, okay, just put it to the GPCC and see what you get. But density there is just soft density.
Yeah.
It's just going around the object. And that time we even laughed that this is hallucinating.
Yeah.
Now everybody talks in AI about hallucination of the new models of intelligence. So can you now briefly say what is your conclusion after all this work? Is density and geometry similar or can it be improved?
So for me, I think it goes back to the discussion that. So for me, I still think they're still closely related, because of the way the function is optimized. Since they're optimized on the final 2D render views, you can adjust the positions of the centroids, and you can also optimize on the opacity values. So what happens? It's in a lesser scale that happen in Plenoptic, for example, but a lot of times there's some information of the geometry that it blends into both the density values, but sometimes even to the spherical harmonic values. So sometimes because of that, as you said, it has an over-parameterization. So for me, I haven't seen maybe the solutions in the last month or so, so maybe they've addressed, and I don't know. But I still think there's a clear separation to the head, for me at least, to when coming from the point cloud side, to properly call them properly separated from the geometry to this kind of density attributes. So that's why I still a bit on the fence about calling them explicit and as the same classification as the point clouds. So for me, it's an explicit radiance field when we compare it to the original radiance fields. But I'm not sure yet if I can call them explicit in the same classification as point clouds.
And what about the hallucination? Can you improve that? Now your final goal was reproduction, PSNR, core PSNR, and so on. And that's how you train it. You paid attention also to the geometry to a certain extent.
Yes.
But could you pay more attention to the geometry so that the densities will become very sharp, very, where is object, I have high density, where is not object, I have very low.
I think so. I think if you could maybe take a measure, if you have the ground truth, for example, with the synthetic data, you could maybe take a measure of the distances between the ground truth and the generated points into the loss function. and somehow try to make it closer to the ground truth geometry, and then we leave the attributes to the attribute optimization to be concentrated on the attributes rather than the coordinates and also the sizes of the splits. So then we could restrict a little bit the optimization to the appearances rather than doing them jointly after it reaches a certain kind of geometry that is, let's say, good enough, at least for a certain kind of representation.
Okay, thank you. I don't have any more questions.
Thank you. Now we go to Christine Guimau for the final comment.
Okay, thank you. No question. No worries, you already know. No, I want to start by first thanking all the jury members for their time and the work they did to evaluate the PhD of Davi. And at the same time, so especially for the rapporteur. So, and I want also to apologize for somewhat chaotic organization that we have to change dates. This has put some pressure on, on all the jury members and also on Davi, of course. And due to some hassles we have to deal with to synchronize the administrative procedures of both universities, which was a heavy thing to do. But eventually I'm quite happy that everything went well at the end and that I will hopefully get the 2 degrees, which is the most important thing in my view. So congratulations, Davi, for the amount of work that you produced, for all the contributions, which were produced in a quite autonomous way. You work on your side, you don't make a lot of noise, but things go well, you progress, and everything goes well at the end. So you're quite easy to work with, you're always very positive, and that was really nice to interact with you. And I want also to say that you've done all that work in an amount of time which is very reasonable, just a little bit more than 3 years, 3.5 years, which is quite a significant amount of work given the time. And also in a context which is, sorry Robert, but not easy context, the Salisbury project, because there are nice environments for PhD students to interact with, because your data set was produced in collaboration with other people of the project, and especially with another PhD student and library. So, which is the nice side of it. The other side, which can be positive, but at the same time, which is time consuming, is the amount of workshops, of training schools, of webinars that you have to attend to prepare presentations for. That was quite heavy.
Yeah,
so,
and there were quite a few.
So this takes a lot of time on the research part. So if I have to convey a message to the
looking at me, I see.
program, I would say that's taking a lot of time on the PhD. So congratulations for that. Davi, you produced, made a great job despite these conditions. So congratulations for that.
Okay.
Okay, thank you, Christine. So now we are going to deliberate. So maybe we are going to stay here.
Yes, you have to stop
là, à côté de lui, pour lui annoncer. Ouais, ou à côté des. On peut se mettre à côté des écrans. Comme ça, on a tous les membres du jury du même côté. Je peux le mettre à côté des membres distants. So the jury, the committee has discussed, and we came to the following conclusion. So we think that you have made a very clear and pedagogical presentation, which will summarize the numerous contributions proposed in the manuscript on this competitive topic of compression of Plenoptic point clouds. So in your work, you have tackled the hot and challenging concept of Plenoptic point clouds. You have proposed original contributions on MPEG GPCC, NERF, and Gaussian splats representations with significant impacts on both scientific and applicative perspectives. You were evolving in the challenging international context of the Marie Curie project, implying the ability for you to accommodate and perform in different research environments in a rather challenging amount of time, around 3.5 years only, leading to a double PhD degree at Tampere University and Université de Rennes. So the PhD committee appreciates the large number of high quality and scientific publications in top-tier journals and conferences, which serve as proof of the originality and competitive performance of the proposed methods. So during the question and answer session, you have provided pertinent answers to the committee questions that covered all aspects of your work, thus showing that you have reached a high level of scientific maturity. You have demonstrated your mastering on the subject field of compression of Plenoptic point clouds that you have worked in, with a deep understanding of the various Redden field representation of 3D scenes, both explicit and implicit. So we don't say which one is when in the report. For all these reasons, the jury awards to you the PhD degree in the specialty Signal Image Vision from Université de Rennes and the PhD degree from Tampere University. And regarding grading in Tampere University, the committee recommends the highest grade pass with distinction.
Thank you.
So congratulations. Yeah. So now do you want to say the oath of the doctors? Now that
Yeah, so, okay, so I started.
Okay.
So in the presence of my peers, with the completion of my doctorate in signal and vision, in the quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. Just have like a few words, not many, because I already talked a lot. So I'd like to first express my deepest gratitude to Professor Cassim and Professor Yuan, because not only valuable guidance and constant support, but also I know it was quite a challenging process with the double degree. I'm not sure if you remember, but when we arrived in France, it was still during COVID. So the first, I think, 6 or 7 weeks done like in Brazil, and then there was a second wave and everything. So, and as you know, it took a little bit more than 3 years, which is expected with the French side. So I thank the patients also the whole process, and I'll also like to thank Professor Robert Blegovich to if the whole procedures, there's possibility of taking on these procedures during this later part of the thesis, especially the side of Tampere. And also Professor Ricardo Queiroz is not here because he had a few medical appointments, but he provided support at different stages of the project, so I'd like to thank him also. I'm thankful to the thesis committee members, so thank you Professor Adrian and Professor Gauthier for taking the time to read the thesis thoroughly and also to make a very pertinent questions and suggestions for changes to my thesis. And Professor Milene, Professor Mark, and Professor Lissonois for taking the time to participate in the defense. And also Professor Aljosas Moritiu, who participated in the CSI meetings. And so special thanks to my colleagues. So in the Sirocco Compact team, so throughout these years, so all the ones that also graduated. The ones at Tampere University, during those 6 months that we stayed there. And all the early stage researchers from Plenoptima, who were part of all those years of the training network. So all the collaboration, the camaraderie, I appreciate all of that. So also thank the European Union, the Horizon 2020, the whole funding process is also important. So without them, the research wouldn't be possible. And of course, to my family, for all the love, the support, and the belief. Those 3 years were quite challenges, so it's also good to have I tore my knee during the process, so I went to visit them. So that's quite funny. So I'd just like to thank everybody and the colleagues, and that's it. Oh yeah, I think because it zooms out.
So you have to tell it again.
So thank you.
Okay.
Thank you, everyone.
Thanks, Adrian.
Thanks for the invitation, and once again, congratulations for your super nice thesis.
Thanks also.
Bye bye, everyone.
Thank you.
Bye.
Bye, everyone.
Bye.
Bye.
Oh, good, it's over.
I'm breaking the news.
So, I sent the email that